Okay, let's unpack this. When you think about AI, you probably imagine raw processing power and endless data, right? But today, we're diving into a fascinating new chapter in how these models truly remember things. And let me tell you, it's a story with some surprising twists. Imagine for a moment you're deep in the lab. You're a researcher staring at lines of code, baffling numbers, and honestly, a truly frustrating problem. You're trying to build a brain for your AI, a really smart one that can remember everything it's ever processed, even in super long texts or conversations. You've poured like years into perfecting what you thought was the future, linear attention models, trying to be efficient. You've built 3 whole generations of them, from simple vector loops to these fancy controlled forgetting mechanisms. Sounded great on paper, but despite all your brilliant efforts, it's like your AI has the memory of a goldfish. I mean, gets the gist of the last paragraph, maybe. But ask it to recall a specific detail from 50 pages back. Blank stare. Its memory score, this thing called ruler we use, it's just stuck. Dismal, like 0-1 to 0.35. Nowhere near the big guys, the transformers. So maybe it's 3 a.m., maybe you're running on fumes. You think, what if I just, I don't know, sprinkle in a few layers of the old tech, the full attention stuff. Yeah, the clunky, expensive stuff you were trying to escape, but maybe, just maybe. And poof, like actual magic or maybe just stubbornness paying off, the memory score leaps. You hit a 3.1 ratio, linear to full, and suddenly you're at 0.42 on ruler, matching the transformers. You almost spill your coffee. Okay, maybe you do spill your coffee. So you go all in. Train 72 models, different sizes, 340 million, up to 1.3 billion parameters. Crazy, right? And sure, your best pure linear model, maybe GatedDeltaNet, looks great on its own. Standalone champ. But then you look at the hybrids, and this HERN2 model, mixed at a 6.1 ratio, comes out of nowhere. It beats your standalone champ by 1.2 points. That's when it hits you. Standalone glory means absolutely nothing in this new, unexpected hybrid land. It's a completely different game. You tweak the ratios again from 24 linear for every 1 full, all the way down to 3-to-1. And language modeling. The AI's ability to just talk fluently. It barely flinches.
Yeah.
Just a tiny hop, 0.55 average score to 0.57. Pretty stable. But recall, it doubles, it climbs, it breathes, it comes alive. And that's when you truly realize. Those full attention layers, they aren't really for fluency, they're for memory. They're the secret sauce for recollection. So you dissect the architectures like a mad scientist, you look inside, and you discover it's not just the ratio, it's the combination. It's selective gating, stopping catastrophic overwrite. It's hierarchical recurrence, holding context at different scales. It's controlled forgetting, curbing state crowding. Miss one of these key ingredients in your linear part, recall crashes. Doesn't matter what ratio you use. It's like this delicate clockwork mechanism. Then, the moment of truth. You plot the Pareto, front efficiency versus performance, FLOPs versus accuracy. Pure linear HGRN sips FLOPs like a fine wine. Transformers, they guzzle them like cheap beer. High performance, sure, but costly. But the hybrids, HGRN2 at 6.1, it sits pretty right there on the curve. Great recall, and it cuts the memory cache needed by like 4x. You found the sweet spot, so you test the guidelines you've uncovered. Pick HGRN2 or GatedDeltaNet, use a 3.1 to 6.1 ratio. Boom. Transformer level recall, maybe half the cost. You're a hero, a genius, a very tired researcher. People say, oh, just linear versus full attention. But you show them the ablations, the experiments where you took parts out. It's the gating, the hierarchy, the forgetting, working together. They say, oh, it's only on small-scale models. You point to the pattern, it's consistent across sizes, from 340 million to 1.3 billion parameters. And then the ultimate realization, you didn't just train a better linear model. You didn't just train a better transformer. You trained the art of mixing them. You built a bridge between speed and memory, between linear efficiency and full attention's powerful recall. That, my friend, is the hybrid truth.
Wow, that's quite the journey. And what's truly fascinating here is that this conceptual journey you've outlined actually perfectly encapsulates the recent breakthroughs in AI, particularly regarding how large language models manage and retain information over really very long sequences. So today, our mission is to take a deep dive into a paper published just yesterday, July 10th, 2025, titled A Systematic Analysis of Hybrid Linear Attention. We'll explore why this art of mixing is so critical, how it actually works under the hood, and importantly, what it means for the future of AI.
Exactly. That sets up the big challenge beautifully. So if you've ever felt overwhelmed by the sheer volume of information out there, or wondered how these massive AIs handle really long conversations without completely losing their train of thought, this deep dive is definitely for you. We're going to distill the essential insights from this cutting-edge research so you can walk away well-informed and perhaps even with a few aha moments. 1, the big problem. Why transformers struggle with long memory. Okay, so let's start by laying the groundwork. The transformer architecture. I mean, it's really dominated the world of large language models. It's undeniably brilliant, right?
Absolutely. It's the engine behind so many of the powerful AIs we interact with daily.
But it has this big Achilles heel when it comes to remembering things across really, really long sequences of text, like
Yeah.
novel-length stuff.
That's right. And if we connect this to the bigger picture, it's fundamentally about something called quadratic complexity. It sounds technical, but the idea is pretty straightforward. Imagine a long document, say a very long meeting transcript, or even a book. For a standard transformer, the amount of computation it needs to do, and crucially, the memory it needs for its key value cache, that's its working memory, it grows exponentially. Specifically with the square of the sequence length. So this isn't just a small increase. It means if your text doubles in length, the memory and the processing costs don't just double, they quadruple.
Whoa, okay, quadruple.
Yeah, and you can see how this very quickly becomes, well, astronomically expensive. It's impractical for memory limits, for processing power, especially as we want AIs to handle longer and longer contexts in real-world applications.
So it's kind of like trying to perfectly recall every single word someone said in a week-long conversation and needing 4 times the brain power if the conversation lasted 2 weeks instead of 1. That's a serious bottleneck for efficiency.
Precisely, a major hurdle. 2, the first attempts. Linear attention models and their evolution.
Okay, so faced with this memory crunch, this quadratic problem, researchers turn to a new class of models. Linear attention. The name sounds promising already.
It does, and their clever idea was to try and compress all that rapidly growing information from the past into a fixed-size hidden state.
Fixed size, so no more exploding memory.
That was the goal. Much more streamlined in theory, right? They were hoping to break free from that quadratic scaling.
So how did they actually try to do that? Did it work right away?
Well, this raises an important question. How did they evolve in their attempts? It wasn't just one single idea. The study we're looking at meticulously outlines 3 distinct generations of these linear attention models.
3 generations, okay.
Yeah. First generation. Think vector recurrences. This is kind of similar to traditional recurrent neural networks, RNNs, if you're familiar with those. An example model here is HGRN. These models typically had just a single vector, like a single summary number, that tried to capture all the important past information. They used gating mechanisms, sort of like little switches, to selectively decide what information to keep and what to forget, which also helped with the old vanishing gradient problem in RNNs.
Right, where the model forgets stuff from way back.
Exactly. So it was a good start, but that single vector, it had limited capacity. It couldn't hold too many different distinct memories at once.
Okay, so generation 1. Good start. Limited memory space. What came next?
Second generation. They got more ambitious. They moved to what are called outer product states with decay. Sounds complex, but think of it this way. Instead of one summary vector, they used a 2-dimensional matrix, like a small grid, as their hidden state.
A grid instead of a line. More space.
More structure, more capacity. Models like RetNet, GLA, and importantly for later, HGRN2 fall into this category. They'd accumulate these things called rank 1 outer products, basically a way of building up associations between different input words or concepts, and then they'd apply a decay gate to gradually fade out older information. This significantly increased their capacity to store and manage information compared to Gen 1.
Better storage? Okay. But still maybe not perfect recall.
Getting better, but yes, still challenges. Which leads us to the third generation. This is where it gets really interesting, I think. They introduced delta rule controlled forgetting.
Delta rule controlled forgetting. Okay, break that down.
So instead of just passively letting old information decay, these models like DeltaNet and GatedDeltaNet actively erase stale content. Specifically, they look at the current input, the key, and figure out what old information is no longer relevant based on that key, erase it, and then write the new associations.
So it's like cleaning out the old file before putting in the new one based on what the new one is about.
Exactly. It's a forget then write mechanism. And this really helps with long-range recall because it prevents something called state crowding.
State crowding?
Yeah, basically the hidden state just becoming an unusable mess of too much old, irrelevant junk cluttering up the limited space. Controlled forgetting keeps it cleaner, more useful.
Okay, that makes a lot of sense. So each generation was essentially finding a smarter, more sophisticated way to compress and manage that fixed-size memory, trying to pack more punch into a smaller, more efficient space, ultimately aiming for that transformer-like memory without the crippling cost.
That's the core progression, yes. Clever engineering at each step. 3, the crucial realization. Pure linear isn't enough. Hybrids are key. But Despite all these advancements, all this clever engineering through the generations, the fundamental fixed hidden state approach in pure linear models still had a major drawback.
There's always a but, isn't there? What was it?
They typically suffered from limited recall performance. They might be great at understanding language fluently, generating coherent text, sounding natural.
So they could talk the talk.
Exactly. But they struggled to walk the walk when it came to retrieving specific, precise information from far back in a long conversation or document. Those details we talked about earlier, the ones transformers could get, albeit expensively.
Okay, so they were efficient, definitely, but still a bit forgetful on the crucial details from way back. Not quite the magic bullet they were hoping for. That's where this idea of hybrid linear attention models really comes into its own, I guess. It sounds like the ultimate compromise.
Precisely. It's about taking the best of both worlds. The proposed solution from this paper, and what's proven so effective in their experiments, is to strategically interleave full attention layers, those original memory-hungry but incredibly powerful transformer layers, with the more efficient linear attention layers.
Interleaving. Like shuffling a deck of cards, but with AI layers.
Sort of, yeah. You alternate between them. So while the overall computational complexity isn't purely linear anymore, you still have some of those expensive layers. The reduced proportion of these full attention layers significantly shrinks the overall memory footprint compared to a pure transformer. And, critically, adding even just a few of these full attention layers dramatically boosts that recall performance we were just talking about.
So you get the efficiency benefits for most of the processing, but you strategically place these powerful memory hubs, the full attention layers, to handle the heavy lifting for recall.
That's the core idea. It's a hybrid approach aiming for that balance. 4. The study's core questions and findings. The hybrid truth revealed.
Okay, this is where the systematic analysis you mentioned comes in. The researchers didn't just throw some layers together and hope for the best. They went into this with some very specific pressing questions they wanted to answer about these hybrid models.
That's right. They wanted to move beyond intuition and anecdotal evidence and really get some data-driven answers. They systematically asked 3 main things. 1, does a linear attention model that performs really well on its own automatically make the best hybrid architecture when you mix it with full attention?
That seems like a reasonable assumption, maybe.
You'd think so. 2nd,
Yeah.
how exactly does the ratio, how many linear layers for every full attention layer influence 2 key metrics? The model's general language modeling ability versus its specific long-range recall. Are they affected differently? And 3rd, which specific architectural components within the linear attention parts are most crucial for optimizing both language modeling and recall in these hybrid setups?
Okay, those are some really fundamental questions, and their findings, you said earlier, were eye-opening. What did they discover first?
Well, that first question, does the best standalone linear model make the best hybrid? What's remarkable here is the answer they found is a resounding no.
How?
A linear model that performs exceptionally well on its own doesn't automatically translate into the best hybrid partner. For instance, when they trained those 72 models across different sizes.
Right, 340 million to 1.3 billion parameters.
Exactly. GatedDeltaNet, which we mentioned as a Gen 3 model, actually had the highest standalone accuracy among the pure linear models they tested at the 340 million parameter scale. It was the best purebred. But when they hybridized it, another model, HGRN2, a Gen 2 model, interestingly, when mixed at a 6.1 linear to full ratio, actually outperformed the GatedDeltaNet hybrid by about 1.2 points on their recall benchmarks.
Wow. So the standalone star wasn't the best team player in the hybrid context.
Precisely. It clearly demonstrates there's a complex interaction happening between the linear and full attention layers. Standalone benchmarks, it turns out, are unreliable predictors for hybrid success. It's not about finding the single brightest star, but maybe finding the one that shines best in that specific constellation with the full attention layers.
Okay, that's a critical insight for anyone designing these systems. So if standalone performance isn't the key predictor, what about that ratio? How did mixing more or fewer full attention layers change things?
Right, the second question. And here, the study found a very distinct and super interesting impact depending on what you measure. First, language modeling, or LM. This is the AI's general fluency, its ability to predict the next word, to just talk coherently. This remained remarkably stable across a wide range of linear to full attention ratios. They tested from 24 linear layers for every 1 full layer, all the way down to 3 linear for every 1 full.
And fluency stayed pretty much the same.
Pretty much. It barely flinched. They saw only a tiny hop in average scores, maybe from around 0.55 to 0.57. So the general language ability wasn't very sensitive to the ratio.
Okay, but what about the memory, the recall?
That's where the magic happened. Recall capabilities, especially measured on those tough, long-range memory tasks like the ruler benchmarks. This improved significantly as more full attention layers were interleaved.
How significant?
Remember those pure linear models stuck around 0.1 to 0.35 on ruler? As they increased the proportion of full attention layers, moving towards ratios like 6.1 or 3.1, the ruler scores jumped dramatically. They climbed towards the transformer baseline score, which was around 0.42 in their experiments.
So they basically closed the gap with transformers on recall just by adding a few full attention layers.
Pretty much, often peaking around that 3.1 linear to full ratio. And the reason is thought to be that near infinite hidden state, that huge precise memory bank provided by the key value cache of the full attention layers. Even a few of those act as powerful anchors for memory. It essentially doubled recall performance compared to pure linear, making the models really breathe with long-term memory, as you put it earlier.
That is fascinating. It means you can have an AI that's incredibly efficient for just general language understanding, using mostly linear layers. But if you strategically inject just a few of those powerful full attention memory banks, its ability to pull out specific facts from deep in the past just skyrockets. So for you, the listener, if you're thinking about building or using an AI for tasks needing long-term memory, summarizing huge documents, maintaining context in long chats, this tells you exactly where to put your computational muscle. It's those targeted full attention layers doing the heavy lifting for recall.
Absolutely. A very clear trade-off and a clear strategy emerged. 5. The critical architectural properties. The why behind the success. But the study went even deeper. They didn't just look at ratios, they wanted to understand the why. Why do certain linear models work better in hybrids than others, even if they aren't the standalone champs? They identified 3 critical architectural properties within the linear attention components themselves. Think of these as essential features the linear layers need to have to be good partners in a hybrid system. These properties are crucial for enabling that near transformer level recall, but with the much smaller, more efficient KV cache footprint of the hybrid model. They are the how behind building that bridge between speed and memory.
Okay, this sounds important. Given how crucial these hybrid models seem to be, what are the specific architectural elements? What features within those linear layers are truly making the difference here and making them such good partners for full attention?
Right, they pinned it down to 3 key things. Number 1, selective gating. This allows the hidden state, that fixed-size memory of the linear layers, to be exposed to a learned, token-wise gate.
A gate, like a filter.
Exactly. Think of it like a smart filter or maybe even a bouncer at a club. It intelligently decides what new information, what new memories get to enter the AI's limited fixed workspace. And crucially, it makes sure important old memories aren't accidentally kicked out or overwritten when new stuff comes in. Models like GatedDeltaNet and HGRN2 really excel here because this gating prevents what's called catastrophic overwriting.
Makes sense. You don't want new info erasing vital old info. What's number 2?
Number 2, hierarchical recurrence. This is something particularly seen in HGRN2. It uses a clever 2-level pathway.
2 levels.
Yeah. Imagine a meticulous librarian. They don't just put every single word on a single shelf. They create coarser summaries of entire chapters, maybe store those at a slower rate, and then maybe summaries of those summaries for the whole book. Meanwhile, the really specific token-level details are handled by a faster, more immediate pathway. This kind of hierarchical structure helps latch information effectively. It bridges the gap between those more widely spaced full attention layers, helping pass information along efficiently and significantly, improving that trade-off between general language modeling and specific recall.
Okay, like having both overview notes and detail footnotes. Smart. Yeah. And the third one?
The third critical property is controlled forgetting. We touch on this with the DEN 3 models. Mechanisms like the outer product delta rule in GatedDeltaNet or something called gated diagonal decay in HGRN2, explicitly manage the removal of stale or irrelevant content.
This is the active erasing part again.
Exactly. It's like a super efficient archivist. They don't just let old files pile up and gather dust. They actively identify and shred the outdated or irrelevant ones before filing the new, fresh information. This actively prevents that state crowding, the hidden state becoming a useless mess, and that, in turn, boosts recall significantly because the space is kept clean and relevant.
Wow. Okay, so It's really not just about mixing the right amount of full attention in. It's about making sure the linear parts you do use are sophisticated. They need that selective gating, that hierarchical structure, and that smart forgetting mechanism to really work synergistically with the full attention layers. And as you said earlier, the research showed that if you miss any one of these key ingredients in the linear component design, recall performance just crashes, regardless of the ratio you use. It really sounds like a finely tuned, delicate clockwork mechanism.
That's a perfect analogy. It's about the combination of well-designed parts working together. 6. Practical guidelines and efficiency insights. And the great thing is, this detailed analysis leads to very practical takeaways. For practitioners, for developers out there looking to build these memory-efficient, long-context language models, the study offers clear, empirically validated guidelines based on all this testing.
Okay, so translating the science into practice, what's the recommendation?
They recommend choosing a linear attention model architecture that explicitly incorporates these 3 critical properties we just discussed: the selective gating, the hierarchical recurrence, and the controlled forgetting. Specifically, based on their results, they point to models like HGRN2 or GatedDeltaNet as strong candidates.
Right, the ones that performed well in the hybrid test. And what about that crucial linear to full ratio we talked about? What's the recommended sweet spot?
They suggest aiming for a ratio somewhere between 3.1 and 6.1, so 3 to 6 linear attention layers for every 1 full attention layer.
3 to 1 up to 6 to 1.
Correct. Their experiments showed that this configuration consistently achieves near-transformer recall performance, getting you that crucial long-range memory capability, while simultaneously, and this is key, significantly shrinking the size of that expensive key-value cache compared to a pure transformer. For example, they saw reductions by a factor of 4 to 7 times.
4 to 7 times smaller cache. That's huge.
It really is. This is where the efficiency truly comes into play. So for you, the listener, if you're thinking about deploying or developing with these models, this isn't just some abstract technical detail. It means you can potentially get that high-end transformer-level performance for memory-intensive tasks, but with a drastically lower operational cost. We're talking far less expensive hardware requirements, lower power consumption, potentially faster processing times for inference.
That's a monumental win, isn't it? Getting close to top-tier performance for potentially half the cost, or even less, depending on the metric. So what does this all mean for the bigger picture of computational efficiency in the AI world? How does it change the landscape?
Well, one way to visualize this is by plotting something called the Pareto front. It's essentially a graph that shows the optimal trade-off between different objectives, in this case, model performance, like recall accuracy, versus computational efficiency, often measured in FLOPs, floating point operations.
Okay, the best bang for your buck, basically.
Exactly. On this graph, pure linear models, like the standard HGRN, they sit way over on the highly efficient side in terms of FLOPs. They sip computation. However, as we discussed, their recall performance might be lower, and sometimes their structure doesn't translate perfectly to high real-world speed or throughput on current hardware like GPUs. Pure transformers, conversely, are way up on the high-performance axis, especially for recall, but they notoriously guzzle FOPs and demand huge amounts of memory. They're powerful, but expensive.
And the hybrids, where do they sit?
The hybrid models, particularly configurations like HGRN2 at that 6.1 ratio, manage to occupy a really attractive sweet spot right there on the Pareto front curve. They offer a much better balanced, strong, near-transformer recall performance, but with significantly improved efficiency compared to pure transformers. This makes them optimal candidates for real-world deployment, where you often need both strong performance and practical efficiency. You can't always afford the pure transformer cost.
So they really do bridge that gap effectively. Outro. So there you have it, the hybrid truth revealed. It turns out it's not really about linear attention versus full attention, like some kind of rivalry. It's really about the art, the science of mixing them intelligently, creating this elegant bridge between the raw speed and efficiency of linear methods and the powerful, precise recall of full attention. It genuinely feels like a paradigm shift in how we approach building these large models.
Absolutely. And what's particularly remarkable here, I think, is that the systematic analysis actually training those 72 different models, testing all these variations, and importantly, releasing the models in code openly gives the whole research community concrete empirical evidence. It shows us how to build large language models that are both highly performant and exceptionally efficient for long context tasks. It moves the field beyond just intuition or scattered one-off experiments towards really data-driven, actionable design principles.
And for you, the learner, Thinking about the implications. This means a future where AI can handle increasingly complex, long-form information much more readily. Without breaking the bank on computational resources, without needing server farms the size of small countries, imagine the possibilities. Truly intelligent assistants that actually remember the details of your conversations from weeks ago, deep research tools that can digest and recall nuances from massive libraries of text, or even creative writing partners that can keep track of every character arc and subtle plot twist across a sprawling, epic narrative. The potential is huge.
It really is. But of course, research never stops. And this raises an important question for the future, something to perhaps ponder. As these models continue to scale even further, maybe to trillions of parameters, and as context windows stretch potentially to hundreds of thousands, maybe even millions of tokens, will these observed trade-offs and the guidelines we've discussed today still hold true? Or will we uncover even more nuanced hybrid truths? Perhaps new architectural tricks or different optimal ratios will emerge at those massive scales.
That is something fascinating to mull on. Where does this hybrid approach go next? We've only scratched the surface today of how these incredibly complex systems learn, process, and remember information, but this deep dive into hybrid linear attention certainly gives us a powerful new lens. Thank you so much for joining us on this fascinating journey.